Most of the work that has been done so far on black holes has concentrated on their stationary states and how these are attained. Apart from two results of Hawking that black holes may not bifurcate and that the area of the event horizon is an increasing function of time, we have comparatively few exact results on the motion of black holes. A supermassive black hole is speeding across the galaxy, and astronomers are baffled as to why. The fast moving black hole, which is about 3 million times heavier than the Sun, is traveling at 110,000 miles per hour, about 230 million light years from Earth. According to researchers at the Center for Astrophysics, Howard and Smithsonian, we don't expect the majority of supermassive black holes to be moving. They are usually content to just sit around. Dominic Pace, an astronomer at the Center for Astrophysics who led the study, said in a statement, "They are just so heavy that it's tough to get them going." Scientists have long thought black holes could move, but such movement is rare because their immense size needs an equally substantial force to get them in motion. Consider how much more difficult it is to kick a bowling ball into motion than it is to kick a soccer ball. Realizing that in this case, the bowling ball is several million times the mass of our Sun, Pesce said that's going to require a pretty mighty kick. Pesce and a team of researchers have been working for 5 years to observe this rarity by comparing the velocities of supermassive black holes and galaxies. The initial study 10 distant galaxies and the supermassive black holes at their cores. They forced on black holes with water in their acceleration disks, which are spirals that spin inward towards the black hole. Pesce said as the water orbits the black hole, a laser-like beam of radio light is produced. When analyzing with a combined network of radio antennas, the light beam known as maser can help measure black velocities. The researchers found that only one of the 10 black holes seemed to be moving, one that sits at the center of a galaxy which is called J0437 plus 2456, but the reason for its moving is unclear. It is therefore of interest to ask whether these results may be extended to the case of black holes. The method of attack consists in showing that if one uses Carter's boundary condition for black holes in well coordinate, one is led uniquely not to configurations looking like particles. One is the aftermath of two black holes merging, causing the newborn black hole to recoil, said Jim Condon, a radio astronomer at the National Radio Astronomy Observatory who participated in the study. The other possibility is that the black hole is part of a binary system. Despite every expectations that there really ought to be out there in some abundance, scientists have had a hard time identifying clear examples of binary supermassive black holes. Pesce said, "Why we could be seeing in the galaxy is one of the black holes in such a pair, with the other remaining hidden to our radio observations because of its lack of maser emission." Researchers said more study is needed to find a definitive cause for the black hole's rare movement. The fact that one is led uniquely to the rod configuration provides a simple proof of Israel theorem in the axisymmetry case. that is the static axis symmetry, asymptotically flat vacuum solution of Einstein's equations containing a compact horizon which is not singular on or outside the event horizons must be Schwarzschild. In the real universe, things get a bit messier, and now a team of scientists led by astronomer Tjarda Bockholt of the University of Aveiro in Portugal have shown their result. It takes as few as 3 gravitationally interacting bodies to break time reversal symmetry. Hitherto, a quantitative relationship between quarks in stellar dynamical systems and the level of irreversibility remained undetermined, they wrote in their paper. In this work, we study quartic three-body systems in free fall initially using the accurate and precision and body code Brutus, which goes beyond standard double precision arithmetic. We demonstrate that the fraction of irreversible solution decreases as a power law with numerical accuracy. The n-body problem is a famous problem in astrophysics. It arises as you add more bodies to gravitationally interacting system. The moment of two bodies of comparable sizes in orbit around a central point are relatively simple to mathematically predict according to Newton's law of motions and Newton's law of universal gravitation. However, once you add another body, things become tricky. The bodies start to gravitationally perturb each other's orbit, introducing an element of chaos into the interaction. This means that although solution exists for special cases, there is no one formula. Under Newtonian physics or general relativity that describe these interactions with complete accuracy. Even with the solar system, which we understand pretty well, we can only predict a few million years into the future. Chaos in the universe is a feature, not a bug. When running n-body simulations, physicists sometimes return time irreversibility in their results. In other words, running the simulations background does not get them to the original starting point. What has been unclear is whether this is a result of the cause of these system or problems with the simulations leading to uncertainty over their reliability. So this is the scientific discussions about the black holes. Either the black holes are moving or not. If you have liked this video, then please subscribe this channel for further video in the future.